Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to answer the question that's on everybody's mind, I'm sure. What is power? So this is about power and what that is. So we have this car sitting here, and we know that this car has a mass m here. I'm just going to put m here. What the actual number is not important for the discussion. Now imagine the driver of the car hits the accelerator and starts speeding the car up. Apparently this car is pristine here, as there doesn't seem to be a driver, but humor me. And our motion diagram for the car, remember the little snapshots in time, might look something like this. So as time goes on, cars going to be moving faster and faster and faster, right? Now let's talk about the free body diagram of the car and why this is. So the car, no doubt, has a gravitational force of interaction between itself and the Earth. We usually put those on the free body and call those something like mg. There's also 4 normal forces acting on the car. So I'm going to go ahead and put these force vectors in. So again, this one is really the cumulative 4 forces, one in each tire in these 2 locations, right? And remember, all force vectors really are the sum of a bunch of other ones anyway. For example, this is the gravitational force of interaction for every atom in the car, attracted to the Earth. Right? Now, neither of these forces are actually responsible for accelerating the car, at least not directly. Those forces aren't doing any work, and they have nothing to do with the car speeding up. The one that's speeding up the car is this. When the driver applies the gas and the engine revs, basically, it creates a torque on the drive shaft. Now, it doesn't matter if it's front rear drive or rear wheel drive for the discussion. Let me assume rear wheel drive. So our frictional force would look like this. Now, that frictional force would be to the right on the car. It would be to the left on the ground. Remember, forces always appear in pairs. That's the force that's involved speeding the car up. And some conceptual evidence of that. Imagine this car was sitting on a frozen lake and somebody gave it the gas. What would happen? Next to nothing. The car wouldn't go anywhere, all right? So it's a frictional force that's speeding the car up. And that force is doing work on the car. Now, as this car accelerates from 1 to 2, that force will have done some work. And if we write out the work energy for the situation, the work energy theorem, the PE1 plus KE1 plus work equals PE2 plus KE2. Now, in this particular problem, we can throw out the potential energies because they're the same. These would go away. And let's just assume that the car starts from rest again. Like a lot of examples here, we'll toss this one too. The work done on the system is then equal to the final kinetic energy. Now, if we're only talking about kinetic energies and the car started from rest, we could also call this the change in energy of the system. And again, there's equalities here and here. And the thing to point out is that the work is equal to the change in energy, and the final kinetic energy is also equal to the change in kinetic energy. Now, anytime you have a quantity changing, a natural question to ask is, how fast is it changing? So like the position of the car is changing, and we define a velocity for that. Rate that position changes, and look at how your velocity is calculated. Your average velocity is change in position over change in time. Right? Now, the velocity of the car also changing, and we can define a rate of change for that. Your average acceleration is change in velocity over change in time. Well, power is another rate of change. Power is the rate that your energy changes. It's actually defined basically 2 different ways. All right, so let me write this down. So power is defined as, I'll write them both down. First way, rate that work is done. or second, rate that energy changes. These two definitions are virtually identical. I'll talk about why I'm using two of them for a moment. In Physics 1, usually you start with power like this, rate that work is done. Notice, again, look at this equation. These definitions are basically equivalent because the work done and the change in energy are the same. So you can define power around this and base your calculations on the work done on a system, or you can define power around this and base your calculations on the change in energy of the system. Definition 2 here, based on change in energy, I like to use this most of the time because I find it to be more general in nature. As we move on in the course, we're going to find that there's other ways to change the energy of a system besides work. You can change energy via a process called heat transfer. And I find this second definition just more generally flows from a more general rate. So anyway, power is the rate that work is done. It's also equal to change in energy, or the rate that energy changes. So equation-wise, all right, we can express this a couple ways. One, power is work. This would be the net work done on a system divided by the time it took. Or we can calculate power by taking the change in energy of a system and divide it by change in time. Either one will work. They work just fine. Now, units, both work and energy are measured in joules. So power has units of joule per second. And like most things in physics, a joule per second has its own little pet name. 1 joule per second is called 1 watt. You're probably familiar with this. Light bulbs are a very common place where you see this. They have a wattage rating on them. Another very common unit of power is in the English system. The horsepower is used quite a bit. And for lots of problems in physics, you'll be asked to convert back and forth between horsepower and watts. Here's the conversion factor. I'll go ahead and put it in the video. 746 watts is equal to 1 horsepower. The technical definition of power, I'm not 100% sure, but it's probably no doubt, they measured the rate at which some horse could do work and defined a unit around it. I have no doubt that's probably where that came from, something like that. So that's my introductory video about power. Oh, I guess I want to go one little step further here. I need to make myself a little room here. There's one more piece to this puzzle that a lot of you will need. So when we calculate power, right, equation-wise, this work over time, and I'm going to drop the delta t and just call it t. And work, remember, can be written force times distance. And these two things here can be grouped together. So power is also equal to force times velocity. Might sound a little strange, but if you look at the equations, this is how it works out too. And depending on how the questions are worded, this may be a more useful way to calculate your power, because like the other quantities like velocity and acceleration of that, you can be asked about average power versus instantaneous power. And up here, these are averages written like this. When you need to calculate instantaneous powers, the power at an instant in time, this is a more appropriate way to do so. You'll find this to be a little bit easier. So that's my short introduction to power. I hope that this helps. Have a great day.